Good evening, everyone. So we will start our session in shortly. Past second session. I'm Geeti Gunamadana, and it's my pleasure to be your host for this thrilling event. Now, I would like to warmly welcome Dr. Prabhani Yanage, Vice Chair, IEEE WIE Sri Lanka section, to present the welcome speech. Over to you, Madam.
Thank you, Whitney. So, an excellent evening and a warm welcome to our distinguished guest speaker and the audience. We are absolutely delighted to have you with us for the second session of the Tech Pulse technical talk organized by the IEEE Women in Engineering Affinity Group Sri Lanka section, co-hosted by the IEEE Robotic and Automation Society Sri Lanka Chapter and the IEEE Computer Society Sri Lanka Chapter. So this initiative uh, aims to upgrade the professional skills and the knowledge of IEEE WIE and IEEE members as well as the general public, and with the aim to enhance the networking among members. So today event is truly special as we focus on into the fascinating world of robotic and deep learning. So our title for this workshop is the design of deep learning for robotic application, an area that sits the cutting edge technological innovations that promise to reshape the future of automations and intelligent systems. So we are honored to have with us Professor Tetsuya Ogata, Director of the Institute of AI and Robotic, Waseda University, Japan, and he's also Professor from Department of Intermedia, Art and Science, Faculty of Science and Engineering at Waseda University, Japan. So Professor Ogata is a leading authority in the field of robotic and deep learning. and his expertise and insight will undoubtedly provide invaluable knowledge and inspirations to all of us. So this workshop is an excellent opportunity for all of the participants to gain a deeper understanding of how deep learning technique can be integrated with robotic systems. So we believe that knowledge here will pave the way for new ideas, innovations, and advancement in the field of robotics. So dear Professor Ogata, thank you for your willingness to share your expertise with us. So your word will undoubtedly inspire the audience. So without further ado, please join me in welcoming Professor Ogata. So I hand over the session to our moderator. Over to you, Gitmi.
Thank you.
Thank you, madam. Moving on with the event proceedings, we have our esteemed guest speaker to conduct the session. Now, I would like to warmly welcome our guest speaker of Tech Pulse Session 2, Professor Tetsuya Ogata. Professor Tetsuya Ogata is a renowned expert in mechanical engineering and artificial intelligence. He received his BS, MS, and DE degrees from the Waseda University, Tokyo. He has held notable positions including research scientist at the Riken Brain Science Institute and associated professor at Kyoto University. Since 2012, he has been a professor at Waseda University and joint appointed fellow at the Artificial Intelligence Research Center since 2017. He is currently a member of the Director Board of the Japan Deep Learning Association and the Director of the Institute of AI and Robotics at Waseda University since 2020. Sir, the stage is yours.
Thank you. Now can I share my slide? Can you see my screen now?
Yes, sir, we can see.
Okay, thank you. Thank you for introductions. My name is Tetsuya Ogata from Waseda University, Japan. So it's great honor to have this opportunity to talk here this Tech Plus series and entitled Design of Deep Learning for Robotics and Applications. So then I will introduce these robots as an application of deep learning. Now then it's called an end-to-end control. So this robot is directly generate motion from the sensor. So with deep learning technologies, but some of the idea is required not to just apply the deep learning to robots can work. So what types of technology, what type of an idea is really important. So that is today's my main message. So now all of you know generative AI dependent by the large language model is become shows great performances on handling the text and sometimes the handling the other types of the modalities. So a few months ago, if I asked to the ChatGPT about myself, so they cannot reply correctly because so sometimes they show hallucinations. So OpenAI said it to avoid to answer such kinds of bad answers. But now when I use Gemini, so it replies very correct answer using some of technique lag or something like that. And also then here, so the Professor Ogata's research highly respected in the robotics committee or something. So now, so it becomes really good. But so the point is that so Gemini and also the latest version of the GPT-4o, they is trained not only the language. They have the ability to handle the different types of modality, like the image, video, audio, something like this. So now this big tech, like DeepMind and OpenAI, sometimes including Tesla or something like that, they now focus on this kinds of multimodal models, so which can handle the image and sounds and something like that. And very interestingly, they almost simultaneously started their project on development in robot systems. Okay, actually, Google has some history of the development of robots, but OpenAI is once quitted continuing robot system 2021. And after that, they released ChatGPTs, and recently, all these groups started to the new project almost from the end of the last year. So almost from this year, some of the very interesting work shown. And here, okay, here's they use some of the technology that you see, so the humans control the robot. And so by showing such kind of demonstration by human the operators, so robots now trained to so as to imitate so such kinds of motions. And that is an approach. Maybe it's okay. Okay, and so. So this one shows history of Waseda University's developing the robot systems. So considering, so now interesting is many big tech now focus on the human-like robot systems, like the Tesla Optimus or Alpha. Alpha is also have the 2 arms, and OpenAI also the work on the Figure 1 or 1X. They also use and develop the humanoid robot. So humanoid robots, so because they now try to teach the robot the human demonstration, that means it might be better to the robot have the similar shape of the humans. So it becomes so easy for the operator to teach them different types of tasks. And considering the history of the robotics back to this slide, so we have the longest history developing the humanoid robots. So Waseda University developed the first humanoid robot. Here, the name is Waseda robot, Wabot 1. 50 years ago. And my supervisor, Professor Ichiro Kato, he started this project, and also his successors. There are actually, Waseda University has many professors related to robotics, and they so far they originally developed the hardware over 300 different types of robot systems. Of course, I don't know, but really long histories. So I believe that our history could be support is so have some combining such a mechanical engineering field and the AI field. So again, the deep learning. So deep learning shows very good performances, especially the image handling, so the sound and natural language processing. But at the same time, we take the focus on the robotics. That means it's still not so easy for user deep learning for such kinds of real hardware devices, applications like robot systems. And it's often mentioned as an Moravec's paradox. So that means some of the tasks the human adult can do, so like the game or logical thinking or medical suggestion or something, such kind of task is easier for the AI than some of the very primitive tasks, like walking, watching, or handling the object by using a finger or the arm or something like this. That's kind of the task is so usually human children can do. But so physically interact with the real world is very, very open and very hard for the robot. So this slide now try to roughly summarize the approaches in conventional research with the deep learning technologies for the robotics applications. And first one is it applied for the recognition parts. For example, robot vision. So robot vision is very important for the recognizing the environment of sometimes target object. for just picking and something like this. This is the very oldest cases. So the target is the deep learning training is to trained to output this rectangle, green rectangle. This means the position of the end effector grippers. So human designer labeled these rectangle to the many different types of object. And deep learning trained to then generate this rectangle as a command to the robot systems. And the other one is so reinforcement learning, deep reinforcement learning. It shows a great performance, especially writing the game, computer game or something like that. Some people believe that reinforcement learning is very also what could be work in robot systems. For example, this one is a very representative task. These two one is a representative example. So in this case, Google prepares 13 robot arms, and they were trained to picking the different types of objects over 3 months. Okay. And here is another task. Google prepared 17 or something. Anyway, many robots to train work at many different types of tasks. It takes 1 year half. So actually, the paper related this work is of which author is a number of authors is over 70. Yeah. Okay. 70 postdoc work on this book. That's very surprising. But so it's a very, how can I say, natural approach from the viewpoint of machine learning people. I understand. Because their goal is usually obtains a model, optimal model by machine learning. Optimal model means so it can generate good output even untrained conditions, generalizations. In that sense, they require a huge size of the data. So it takes sometimes 3 months, sometimes over 1 year, or using simulation or something. But simulator is so actually there are really big gap between the real world and simulation. So sim to real is still very hard problem, almost impossible to solve, especially case of considering manipulations. So now the walking robot, biped walking robot is a good application for the deep reinforcement learning because it's okay to modeling the robot only the robot. But if we need to consider to the object like is it flexible one or rigid or something like that, in that case it's very hard to simulate it or modeling in the simulator. Okay, so now I'd like to the back of the sensor to the robotics, and also it's include in the sense of the cognitive neurosciences. So in the robot, so it's impossible to the model the environment robots, and usually we use a feedback control. Okay? So we, robotics researchers recognize the gap of the model and the real world, and always try to change the talk or command to keep the target trajectory. Okay? So that means we should recognize, so even so with a huge size of data, we cannot obtain perfect models. So we always have such incomplete models, okay? So so it's not so common still, but our target, our approach is, so now I call it deep predictive learning. It is approaches to the online uh, reasoning, to reduce the gap between the model and the real world in real time. Okay, so back to another concept of robotics, behavior-based robotics or soft robotics. They mention that so the important thing is not brain. Important thing is intelligence, not intelligence. So the important sense is coupling between the environment and the body. So passive walk model. Passive walk model is just link models without any motors and computers, but which shape is same as a human leg. And once we put such a just a model, link model on the ground, it's so automatically it can generate walking motions by using gravity. So neural function, so they sometimes use an oscillator, very simple neural model, but an oscillator could be coupled the robot body and the environment, then the walking motion is generated. Here is we should recognize that we don't need such a huge size of the neural models. Deep learning is quite hard, huge models. But for the just control, thinking the control the robot systems, we really consider about the couplings of the neural dynamics and the robot hardware and the target environment. So here is our first paper which described such kind of concept over 10 years ago. And so this idea is very related to some latest concept called as active inferences. So the inferences actively. So then some experience, so the kind of the data, multimodal data is given to the not passively, by active. So by generating this one motion, some multimodal data, multimodal experience can obtained. So this kind of an idea is now is seen last year I had a keynote at the international workshop on active inference. But here is attendees come from the many different fields, but not from the robotics. That is very interesting. So here, so you don't need to understand the old this slides. So, but I'd like to say that here ideas of free energy principle. This comes from the base idea is so we should recognize regarded brain as a predictor. So it always has some expectations to the outward, and so it also recognizes gap of the real sensors such expectations, and it changes the posterior beliefs. So by changing the cognitive states and also the weight of the modeling learning. And also this includes it can change its own actions. This concept is very important. So now I try to explain some simple this kinds of the cartoon. Okay. Now he try to recognize the outer world, and he seems to be a little bit confusing because his internal models he expected the sceneries like this, but actually he recognized here. So now it's on the US side, but this is the EU side, okay? EU Africa side. So how can we deal with these conditions? How can we reduce the prediction error between his internal model and the real such an observed world? So there could be three explanations. One is, first one is here. So if there are machine learning people, they said you need to increase the training data. Because this Earth model, of course, 3D object. So we can take the picture of from the many different directions. So we can collect the many data, many images, and it could be reconstructed 3D models in the deep learning models by using enough technology or something like this. But now we think about he now has confusing. Don't have time to train the model. Okay, so in this case, we have two ways. One is by changing the cognitive states. So if the target goal is just to recognize Earth models, so such kind of differences, so geometrical differences, not could be so not becomes serious problems. So he can recognize Earth models without, so by ignoring some such kind of differences. So by changing the internal style, by changing some kinds of illusional perceptual conditions, he can accept this error. And the other one is he can change the world. Here is a very direct reason he directly rotated the Earth model, but it's okay just moving around or change the viewpoints or something like that. That is could be one of the solutions. By changing the action, then the sensory input could be changed. The feedback control is also included here. So we try to implement this concept into the robot by combining some different types of deep learning models. And it's also a little bit confusing the slide, but okay. Here is a neural models, and here is an outer world, external world. But the external world here means not only the world, and also it's include its own body. Body is also regarded as a target for the predictions. And this part is so we call the fast dynamics neural networks. So recurrent neural networks, he's applied it. So it's okay, you can use a transformer or something like this. But I basically like the recurrent neural networks. And as you know, some of the latest models of the recurrent neural network, like Mamba or something like this, I believe that they will work to such kinds of the way of the recurrent neural network in near future. But anyway, okay. So here is a networks always try to short-term future, and so which target includes proprioceptions, also body motion, body conditions, and also exteroceptions, the world. And then the proprioceptions and the prediction of proprioception is reflected in the actual motions, okay? And it influences the environment and body. It could be changed the environment. But there always have some prediction error. It's impossible to reduce the prediction error to zero. So then this error, prediction error, becomes a kind of the input to this fast dynamical neural networks. And here there occurs some kind of coupling between the neurodynamics and the body and the environment. But if the error is too large, so sometimes it's impossible to reduce the error only this fast dynamical model, then its errors bottom up to the input to the here, more higher levels. Here is we say the slow dynamical neural model. So it has some restrictions. Neurons are activated very slowly. Okay. Some of the sparse connections and neural models, then synchronizing and the dynamics become very slow. That is very similar to the dynamics of the human's brain's frontal cortex. And here is, so networks always try to predict the future. That is corresponding the expectation, intention, sometimes could be called gold. And always higher level networks gives some restriction to keep this gold to the fast dynamical neural networks. But if once error becomes too large, it influences the higher levels. Then the networks change its own goals. This is a kind of concept of our prediction learning models. Okay, so now I try to show you that it's really possible implement this type of model into the robot. First example is here, holding task. So actually it's done is over 80 years ago, very old works now. But so now you can see we made the robot trained by using teleoperation. So now DeepMind and Tesla, OpenAI, they all of them take the same approaches now. They now almost spoiled the deep reinforcement learning, and instead they use this kind of ways. Now we sometimes called imitation learning. And the strength of our approach is that it's collected quite small data. It's okay. In this case, just we said only 50. Okay. Back to the reinforcement learning, they requires 800,000 picking motion or something like that. It takes 3 months. But now we are just using only 50 motions by human operations. And the networks trained to predict the future states. So cognitive states and actions. Action here means joint angle. So it's directly predict the joint angle. That means that we don't need to use such a kinematics of the robot models. So we don't need to calculate the inverse kinematics or something like this because the human directly operates the robot, and that explains directly trained here. So it can generate a joint angle directly. It's very easy to train. And it enables to generate a motion from the pixel to the pixel and pixel to the motor. And here you can see, this is actual image, and this is the result of the prediction. And only the 50 training data, so not so many data. So that you can see the prediction itself is not perfect. There are unclear boundary between the towers and the disks, but it's okay. This is his cognitive state. As a result of the coupling of the neural model and the robot and the environment, and in this case, the towers, then this image, this cognitive state is generated. It could be kind of a hallucination. But by generating a kind of such an illusionary image, illusionary cognitive state, then robot can consistently generate their motions. That's very important. And here is output motors. So the dot line is trained data. But here we put the towers in untrained positions. So that means the robot have to adjust their motion to reduce the prediction error. So as a result of the coupling, since you can see each motion is slightly modified to adapt to such of the changes and positions. So here is some of the outputs for tarot holdings. So you can see it can generate a motion quite promptly. So conventional robot requires to, if we try to apply this kind of motion using the conventional robot systems, then we need to module for the object recognition, object shape recognition, and need to calculate its place from the cameras. And so need to calculate the inverse kinematics of the arm to reach such a target handling positions, and or something like that. So many. But you can see the robot now generates a motion from the pixel to the motor directly, so that it generates promptly generates a motion. And you see then the robot now is handling the book. This is unknown object, untrained object, but no problems. This is shows a very good adaptability in the case in the unknown training conditions. And here is an advanced version we can apply. And sometimes, of course, the model itself is a little bit complex, becomes complex. But basically, the same policy, we can enable the robot to handling this kind of small clauses. And then we show these demonstrations, multiple exhibition in Japan, also sometimes in Germany. And some of the company shows an interest in our technologies. And we exhibited these robot demonstrations in a multiple exhibition. Also, some of them, you can see here is a logo of the products of the Japanese company. So some of the technology now have already released to some industrial lines. And especially some of the interest in, for example, this story is written in Japanese, but a multimodal AI robot. This is a very fast prototype on showing collaborating with Japanese companies. So they firstly replicated to our first works and holding towers, but a more complex way. This is now generated. So here is a real image, and this is a predicted image. Now you can see, so it shows almost same performance in recent generative AI. So it's always keeping the generated image in real times. And so without any procedure programs, any programs, a robot can adapt on the changes and the condition of the target object and automatically adapt by continue to and can continue the work. And just changing the training data, same robot can work on a different type of task. Here is picking the salad. And the teaching the ways and we use virtual reality models. Now he shows a demonstration to the robot. Then robot can recognize an object or something. And the important one of the important topic here is that so now the robot have the torque sensors in the wrist. So the target of the prediction is not only the image, it's also the try to predict the torque of the wrist. So it's very helpful, especially picking the salad, because you see so from the robot camera, there often happen occlusion. So robot cannot recognize the salad, so it's really hand grabbed or not. So by detecting the torque, the force in the wrist, then robot so keeping the picking the salad. And here the same techniques by combining the image and the torque of each joint, it can measure the powder very precisely. And this motion is also demonstrated by the humans, and it can show the very, how can I say, some small motion to control the weight of the powders. So here's why this is it becomes an application. So the line is considering to the development process of the medicine or cosmetic. And I had some of this kind of the medicine, the powder is very expensive and sometimes very dangerous. The humans usually operated this kind of work, but it usually becomes a toxin, so not so safe task. So now many industrial companies use a robot for the such a development line. And the same thing is measuring the liquid. It's also used for such kinds of the medicine or the cosmetic industrial experiments. And here some companies staff and try to test it to the ability of our robot. And it's just train the liquid, two different types of liquid. But they confirmed to the, is it really measured to the other types of the material, like the beans or rice or pancake mix. And so firstly, to shake it. So by capture the image during the shaking, it's also the help to the recognize the size of the amount of the liquid. And also viscosity also could be estimated. And here, which one is the first three? Did I forget? But sorry for the yes, here the pancake mix, they set to the 50 grams to measure 50, but here you can see 50.06. And here is 150 and 100.04. And here is 200 and actually measured 100, 200 and 199.93 and 97. Okay, very precise. So this kind of work done by using only deep learning. All control is so joint control is generated from directly from the sensor input. That is very important. And then again, it's already released to another product by TensorWave in 3 years ago. Okay, so I'd like to show from now not to mention about the detail of the technology, but shows some of the applications. And here is work on also measuring or peak, I guess, pouring these kinds of materials and gradient. And it's won the Best Paper Award in Cognitive Robotics and IEEE. IEEE is biggest robotics conference in IEEE. Maybe some of you know. And so here is a target is so very confusing, many different types of target. And this is actually camera image, and this is a predicted image. And here, very important thing that is we implement is an active perception. That means so that it recognizes objects not only using image, but also then so using the tactile information by then so interacting with this object. And the architecture is very similar. So then it inputs the image, and it also then includes the motor angle and the torque sensor, force sensor implemented in the hand. And this also becomes the target of the prediction. So the networks trained to predict the future image. As you see, so it's very similar architecture with the recent latest generative AI idea. But we proposed this framework much before the generative AI. And the robot network trained using this object. And we tested this kind of untrained object here. So then after training, we can so analyze latent space of the neural networks. And actually, it's not promised, always not promised to the, we can found this kinds of the representation in the neural networks. But here, in this case, we successfully find some very interesting representation in the neural networks. Actually, represented here, the slow latent spaces. So as I mentioned in the beginning, our framework, so slow dynamics parts here. So here, so we can see some of the representations and this robot acquired. Then principal component analysis. So actually, PC1 is of course has a largest contribution to the represented spaces. But here we found the PC2, PC3 generates the spaces to represent each target object like this. And also there are a clear boundary between which tool. Actually, robot needs to select the tool corresponding to the type of each foot. Then here is we can see the boundary to which type of the tool should be selected here. And also this direction means so the controls this as an angle to the during the pouring. That is a very clear representation we can obtain. And that is again also the recognize objects not before the handling. Maybe so machine learning people really like the image processing. I know. So image processing is very important, I understand. But if we consider the applications, the real robot system, real world, we don't need to stick on the image processing. We can use the tactile information by the contacting physically. Then we can obtain much information about the object. So after the handling, after the active perception, then robot recognize object. And here is a result of the case of the untrained target, untrained object. We can find that so network seems to be has a good generalization ability for this type of untrained object. And here is stage of the robots and task, and with showing the success rate. So by combining all information, so image and force and tactile, then we show the best performances. So of course we can, if we introduce the latest spiral image processing systems, this performance could be increased. But again, we should recognize the importance of this kind of tactile information for the robot task robot real applications. Here is a short list shows some of the small demonstration with hand. So this hand is developed by Waseda University, and the important topic feature is that it has many tactile sensors, almost 400 tactile sensors in the hand, and it can detect the normal forces and also shared forces. And by teaching the operation of the picking up the object, then the robot can handle the many different types of objects. And also it's very robust to the interruption of by humans. This motion, so after the interrupted, so robot hand can adapt it to the interruptions. But is very, how can I say, this is an untrained motions. It's automatically emerged by the robot. And with an input of the object, then the excuse me. Okay, maybe then there are questions. Is it okay to answer here now? Could you not argue that the use of the force and tactile information is simply a different approach in controlling the problem, but using image analysis processing to do something initial? Could be. But now then again, I would like to say so importance of the tactile senses. So maybe, yes, just a moment, I need to understand the question clearly. But simply different also so the completely sometimes the different features we can obtain, like slippery, is it slippery or not, or some of the weightness, or so completely different aspect can be obtained by using tactile informations. So especially concerning the handling of the object, this type of information is very important. That is my point. And here is another, so maybe some of you knows him. So Jensen Fang, he's the CEO now of Nvidia. Nvidia now becomes the second largest company in the world, right? So I really surprised. And actually, we executed a robot 3 times so far in the GTC conference, GPU technology conference. And sometimes, yeah, I have many photos with him. And here is, and so this one is, I already shown you to them, so wearing powder. And here is another example. So by using end-to-end manner, then we can control the whole body motion of the robot. And this one is already published at Science Robotics. Science Robotics is so one of the top journal in this robot field, of which impact of factor over 23, now it's in 27, 28, forget. But so considering to the impact factor of the entropy, the transaction, or RAL, or then they less than 10, then this one is quite large numbers. Of course, I prefer to publish the paper in an iCloud or something, but this is one of the challenge. And here you can see our research selected the cover of this issue. And here again, so now we use some multiple combinations and predictive learning. So we prepare 6 predictors to predict the future conditions for the approaching door and opening door and passing doors. Then each module is competitive, and so one is becomes a winner. One with the smallest prediction error is becomes a winner to control the whole body of the robot systems, and it shows quite stable motions. So maybe some of you know, and I will explain. I will introduce later, but we showed this demonstration at ICRA this year in the exhibition site. So you can see the multiple interruption, but the robot can consistently work like this. And this is untrained door. So this is using manner of the mixture of experts. So these multiple predictor is or in parallel try to predict the future conditions, and one of them is take the whole body controls, something like this. Okay, so the other example I would like to show you the opening zipper. So opening zipper itself seems to be an easy work, especially for the human children. But the robot system is not so easy. I believe that completely automatically opening the zipper is still very hard problems in the current robotics conventional robot systems, because it requires not to just adapt to the force, it needs to change the trajectory according to the conditions. Especially in these cases, we started an opening zipper from picking the zipper part. That means so the gripper's condition, so grasping conditions always changes. So the robot needs to adjust to such kind of the change. And the teaching is done like this. So here we just only 36 motion data. Then it can open the zip even different types and back. And we added here new mechanism of the attentions. That means, of course, during the prediction in the future, but we added the networks to the ignore the not important part. So we have some restriction of the predictable version. So now the networks have the constraint. So and they need to select to the which part is can be predicted to reduce the whole image prediction error. So here you can see this red point is automatically trained, automatically emerged as a result of the training. And thanks to these functions, we can easily change the back color, the environment conditions. We can add the many objects. We can add these different objects. And change the color condition, lighting condition, but it's easily adapt to such kind of the change of the environment. And here you can see that is very, I like this scenery. This is this scenery shows the robot can adapt to change of the positions, but here I'd like to say that here is an attention. So we give to the target object by using a language. But here the robot recognize this one. That means so you can see predicted image. Only the target object is predicted, and the other object. So this is completely ignored. That is very important. So not predict the future image perfectly, not needed. And also, if the robot can recognize anything, many things, that becomes a worse effect to the complete task. We can focus, but it can say that we can ignore the others. Okay? That is very important, maybe the lack of sensors and the latest deep learning models. So for the conducting the task in the real world, this kind of the attention is very, very important. Again, here is the target is predicted for cognitive state, including the image and tactile senses and the motion actions. But here we have the restrictions to the predictors. So the predictor have to select which part is important to reduce the whole image error, whole prediction. So that means attention goes to the moving parts, and also then it also needs to relate it to the actions. Okay. So there are many parts it dynamically changes, but some of them cannot be predicted perfectly. But some of them can be predicted because it's influenced by its own actions. So as a result, the attention point is mainly focused on the caused by its own motions. The dynamic changes caused by its own motions. That is a very important sense. And Here is another example by advancing our technologies published 2 years ago. Here you can see the robot trained to pick an object a little bit far, so beyond his arm ranges. And here, so after training, this is untrained condition. Robot recognizes it and removed something like this. Here is very important. So that is an attentional point. Then it comes from like this. Okay, so here, this one, I would like to say the attention, how the attention, sorry, how attention changes. Firstly, so the robot seems to recognize 3 objects. One is a target object, one is a tool, and one is its own hand. And this is just an attentional point. Originally don't have any meanings. These so name is labeled by him, but originally don't have any meanings. Okay, and but an attentional point names one is basically come here. But once it picks the tool, then you can see, okay, one. So gripper path goes on to the head of this object, so tool. Of course, there are many ways to how can we interpret this phenomena, but we can say that our body, the robot body, could be enhanced to the edge of the tools, so tool body assimilations. This is often observed in monkey's brain activities, but the same phenomena is happening as a result of the training. We don't add any program. We just give to the mechanical mechanism of the attention and also training data. But as a result, such kinds of phenomena is automatically generated. So this is very I prefer this one. And so by adding the many objects as noises, it's don't influence, but it can use a different types of tool or something like this. So again, back to the original discussion. So many people, of course, take reinforcement learning. The reinforcement learning, of course, very important way. One of the application, especially legged robot, is showed quite great performances. I know, but at the same time, so we should recognize, and so optimize is not always promised. Okay? So model free or model based, and sometimes model based they use a very similar concept of us called world models. And the world models is trained to predict the future conditions. Okay, and once it obtains the perfect world models, then the policy is searched. The policy learning is conducted in such learned world models. So it's always promised optimized actions is obtained in the such we call under some restrictions and optimized world models. Models. So we think that we never reach the perfect models. Always only have the incomplete learning. So always have the gap of the real world and the models. So the actual motion is always selected to reduce the prediction error. Then such kind of the sense is automatically generates goal-directed motion. That is our senses. So that means that we cannot promise that it obtains a perfect model, optimized motion. So in sense, it always takes a habituated manner. For example, it's often we can see in humans. If once becomes a right-hand user, I'm right-hand user. Okay, so when I pick the object in the right side, of course I use the right hand. But even the object placed in the left side, I usually take the right hand. I know left hand is much might be better to picking the object on the left side. Okay, but I usually use the right side. Okay, because I habituated this. So considering the reduce the predictional error, I'm not so good at using the left hand. So by increasing the training data with the left hand, so I can use the left hand. But so if we have the incomplete models, so as a result of the selection with a minimum prediction error, then I use right hand. That is our sense. And maybe 30 minutes more. Okay, but yes, I try to explain as much as possible. So the other target is the language. And so large language models, of course, shows very big performance that I know. But I'd like to say something about that. Okay. So it's okay. GPT-4 or something like this. So if just a conversations, something like this kind of application, that kind of large language model is now becomes almost perfect models. Okay. But now if we think about the use of that model for the real world application, we need to think about some of the problems like the symbolic learning problems. For example, this is just an example. There are many huge number of the programs for the considering the gap between the real world and the sentence and the languages. So one is such kind of ambiguity. So one motion can be explained in many different types of sentences. Touch the one, touch the orange, touch the one in front, hand on that fruit, something like this. But of course, on the other side, one sentence could be represent many different types of motion. And it's okay to explain it using by two sentences. So close to the orange and touch it, something like this. Okay. There are the many variations to by combining these two aspects. By using some technology like the clip, it could be some of the puzzle is actually solved, but still have the very hard problems. Here is that shows our old studies and over 6 years ago. But we introduced almost completely same idea of the clip here. Okay, so here is two autoencoders. So encode is the action parts. So as I shown in such an motion generation motion learning, prediction learning, so each joint and the visual image is embedded in the recurrent neural networks, and here is a latent space and decoded. And here is so corresponding the sentence is embedded here and decoded. And so here is the training also have the losses. So the corresponding motion and the sentences of which latent space is trained to the closes each other. And the different one is far separated. Yes. And now it's called a kind of clip, but this kind of the idea is proposed now, maybe at least 30 years ago. Very common idea is neural networks models. And here, this is in a very simple settings because 6 years ago. But the robot trained to handle the object to the left side and the right side, and which is described using different ways. So by using a position, left and side, right. Also, sometimes it's called using its color or something. And here is the different types of motions, and pushing it, pulling it, or sliding it, and also slowly and fast. Okay. So there are so two ways, and the instructions more language to the action, also the action to the language. So number of sequence data, so such kinds of small toy world, but if we considering all kinds of the combination of the motion and the object, then in total is over 400. But actually we cannot take the all kind of the motion, of course. So just 54 patterns trained, and we tested 18 patterns here. Okay, what happens as a result to the considering such a many-to-many mapping, many-to-many mapping? How the networks embedded it? So again, so such a small data set, small models, we can recognize, we can see the representation in the latent spaces. Here, we check here, this one. Yeah, almost similar structure was here, of course, but firstly we use here. Then here is a map. Then so actually, here must be over 54, 55. I forget the name of number of the sentences, but many many more sentences described here. And we just selected such kind of number 18 number untrained cases, untrained situations. So this one is we can choose, for example, same map here. The sense of its sentence includes these words, slide, push, and pull. Okay, you can see the similarities of these slide, push, pull. So slide, it is used in many different contexts. Slide right side, slide green object, I don't know, but many objects. So, but so that means that there is no single representation of the slide. Slide is used in many different ways. But we can see that so slide, push, and pull is same in the sense of that this geometrically conditions. Okay, here the same map. Same map is when if we see the sentence is including a color, then yes, you can see the same geometrical combination structures. And the same map, we can see if we compare the fast and slowly mapped like this. So by using the latent space is continuously and also could be enhance many different directions. So it can embed it, some of the complex structure is kind of geometrical way. I can say that it's a perfect representation. It's an okay representation. I don't know, but it's the kind of the interesting characteristics of the deep learning models. And here again is this is a representation of the action. And by using clip, then is a representation you can see them so almost same position. So by reducing the error gap between the sentence and action. But so of course one sentence could be represented many different action sensor becomes like this. But if we don't use such kind of clip binding, what happens? So result becomes like this. Actually, motion cluster itself now acquires self-organized. But now we recognize, found that so these structures, these action representation completely ignore the visual information. So they make the cluster just focusing the similarity of the action. So by binding, so clipping with the sentences, then the visual information can be used. That is one of the interesting result. And here is another example, introducing the trained language models. So published 2 years ago, but just before the ChatGPT. Then we use the same architecture of this one 6 years ago. But for using trained model, in here we just use Word2Vec, one of the smallest language models. But that word is represented by the vectors, and it's include some of the sense of the semantics. So we expected the robot to recognize untrained words, untrained sentences. But we found that so that representation cannot be used directly for our training. So we need to add this layer, retrieve layer, for transfer this vector, Word2Vec, to our embodied models, embodied AI models. So we use the data set of this kind of human motions, capture motions. Actually, I would like to use real robot data, but in this case, the language models we used, so we need some size of the data set. And here is one data set, captions and motions. And so almost 4,000 motions and which captured by the humans. So some of them have the 2 or more 3 captions. Then the caption number of the caption is larger than the motions. And we trained this network, the previous networks. So we need such an couplings, bindings, or clipping is okay. But we just using 500 pairs for training. And this is enough to transfer the motion to the sentence or sentence to the motion for these all 4,000 motions. That's very interesting. And as a result, this is original. So one motion is captured like this. One of them is 2 or 3 captions. And by using some original one, so without without word to back, then of course our model is a person jump forward or a person push from the right, actually something like this. By using the word to back, then by using semantics, then the recurrent networks decoder, language decoder can generate more and more detailed explanation about the motions. This is surprising, was surprising for us at this time. Just 2 years ago, but 2 years ago is before the ChatGPT, is a very, very surprising result. And of course, opposite one. So by input and sentence, it can generate the motions, something like this. Dancing or something. It is a very, very generalized. Now I would like to explain why retro-read layer, this layer is required. So here is just a similarity, cosine similarity is originally embedding the word to back. And of course, there are many words, of course, but we just focus on here. So, so you can see there are, of course, clusters. Okay? But here is the clusters means syntax, such as grammatical rules. So by applying the retroactive failure, they generate more and more detailed clusters. For example, slowly and fast, from the viewpoint of the sentence, grammatically rules. So slowly, fast, and the same, almost the same. But for generating the motion, slowly and fast is completely different. It's a completely opposite meaning. Here, so actually I skip the explanation, but you can see, actually this is pushed from the not right, pushed from the left. This kind of confusions sometimes happen. And actually caption is to the right, but from the right. Okay? Here is from the left. So so little bit confusing, but left and slowly, first of all, sometimes so the word is very similar, the sense of grammatically, but completely different in the real world. That is one of the problems. Okay, so then maybe from now I'd like to mention about our latest activity. Related to the Japanese government project named Moonshot. So so now we can imagine it comes from the rocket project in the United States in the 1990s. And so there is a president who says we take the human to the moon, and till end of the 60s. And at that time, everyone thought it was kind of the dreams, but they finally realized. Then these kinds of the names, so we make this very, very big goals and try to reach them until 2050s. And there are in total 9 goals, and each of the goals has quite big budget. Sorry, I cannot translate to into the other, but anyway, so very huge size. And goal 3 is related to robotics and AI, and of which in the head, project director is Toshi Fukuda. He was an IEEE president uh, 5 years ago. I forget when, but yes. He was only one president outside of the North United States. So that is also one of the our pride in Japan. And our group, of which project manager and Professor Shigeki Sugano, he is Dean of our Faculty of Science and Engineering, Waseda University, and also now the steering committee chair of the IROS. IROS is one of the largest international conference on related to robotics. And basically, proposal is written by me, and I thought that so realizing to the types of smart robot, each follows the same flow of the development of the smartphone. So smartphones originated these types of dedicated machines like camera, games, dictionary maps, or something like that. And of course, there still remains this kind of specific devices. And the smartphone has these kinds of the function. But if you just compare to the performance each devices, of course, so smartphone cannot be on any other devices if just compare such a one single functions. But once this function packed to this one devices, the size of the market is much larger than the summations of these dedicated device machines. So I believe that robotics will follow the similar ways. Actually, I proposed this idea over 7 years ago. This project started 4 years ago. So just thinking the history of the humanoids, so we can believe that humanoid can do the many things, even one bodies. And I think from this year, so as you see, there's an OpenAI, Tesla, and other type of many robotic, many big techs seems to be think about the same thinking. So Optimus can many tasks, and one X Neo can work the many different tasks. So this kind of idea now becomes the same senses, common senses in the world. Of course, it's kind of the dreams, especially in Japan. So we had experience to develop an Ashimo 20 years ago. That time, so Ashimo or other type of the humanoid, many developed types of humanoid developed at many different types of companies. But finally, almost them failed to make the market of the humanoid robot. So in Japan, it's very hard to then propose this kind of project. But now, from this year, now the United States and China had quite many activity for developing a humanoid robot with AI technologies. And here is our latest version of the robot, humanoid robot. The name is IREC. IREC is come from the name of AI-driven robot for embrace and care. It's a little bit wrong name. But anyway, so we expect this robot can work in many different type of scenery for supporting the human daily life. And it can generate big power. So even using one arm, it can bring up over 20 kilograms. And at the same time, it has a torque sensor on all joints. So it can generate very smooth motions like this. Here we don't use any AI. We just input the impedance with the zeta director axis to keep the same, something like this. And here is one of our latest result of the cooking. So cooking, first, so Saito-san proposed this project. She is the first author of pouring food. It's won the best paper of the IEEE. Yes. And she continued the work on the cooking. And scramble egg, as first I thought that it's easy. It's okay just moving the random motion. But if you do so, the result becomes like this. Yes. It's not so good. So in this case, she taught the robot by using direct teaching. So since she cannot explain what she doing in detail, so that means that she cannot program it. But by teaching 20 times or something, here 32 times, 32 times, then the robot acquires her skills, and automatically changes its motion according to the condition of the egg. So egg condition is gradually changing during the heating. Okay, then the robot needs to change its manner. And also we are the attention. Here we use not attention not just for the vision. This attention is can select each modality. Then the first condition is mainly focused on visionary, but during the cooking, attention moves to the tactile senses. That is very interesting. Now we have submitted this paper now. Okay, so here is open source software is our deep predictive learning. So we called it not deep reinforcement learning, deep predictive learning. Okay? And one of the way to apply the imitation learning. So some simple attention mechanism also implemented. So you can try it. If you are interested, please capture this image now. Here is one of the latest demonstration of picking the object sensor, so you can see that even changing the lighting condition or adding the human hand noises, robot can consistently to the motions. And here is a demonstration as exhibition last year, last December at the Tokyo Big Site. Here is an ministry. Former minister is come and visit and shows our demonstrations. Just a moment, sorry. Okay. And here now we started collaborated with multiple university, one of the technical university of Munich. That demonstration is a collaboration work with postdoc from the Gordon James Brown. And from this April, we started the collaboration with an Alan Turing Institute, with a famous institute in UK, so National Institute related to the AI. It's famous and DeepMind belongs to this institute. And I have the friend of Sensei Vijaya Kumar. He is now the head of the robotics section of this institute. So we had a MOU, I mean, the MOU between the Turing Institute and Waseda. So I think there are some stories. How is the robots and AI is co-evolved? Co-evolved means that now, interestingly, many companies restarted to develop the humanoid robot. Again, humanoid robot is developed from 50 years ago, and over 20 years ago, there kind of the boom in Japan, the humanoid robot, but always it failed because we can develop the biped walking, we can develop the arm and fingers, but there's no way how to control control whole bodies. But now we have the AI. So some predictive learning based on imitation, skill transfer, human skill transfer. Then some of the work can be done. So we expected to then, develop some of the types of robots. Then the boundaries change. So boundary means so AI, for the AI is such an interface, the function of the interface and kind of the boundary. So by enhancing the robot abilities, AI could be enhanced. So by enhancing the AI technology, we can reconsider about designing the new types of robots. So this kind of interaction is very important. So I call this co-evaluations. And also now we need to consider about social acceptance from the viewpoints of the LC, ethics and legal and social acceptances. So the AI alliance is one of the big issues of the AI development system. So robot shows a more big impact if it applied to the real environment, real world. So we need to discuss with such kinds of research on the social scientist. For example, 4 years ago, I developed an established institute of AI and robotics at Waseda University. Here, I asked many professors come for the mechanical engineering, also the information technologies. Information technology means work on the image processing or natural language processing or speech processing or something like this. But at the same time, I also asked many professors from the social sciences and sometimes human sciences. So, of course, commerce, business is, of course, very important aspect, one of the aspects of AI and robotics. But at the same time, we need to think ethics and also thinking law and also how it influences political and economic conditions. And Waseda University has many school related such as law and social science and political science or something like this. So I believe that this kind of the collaboration now becomes a big important issue in the future. And almost now is the end of my talk, but last few slides I'd like to introduce a demonstration at ICRA. ICRA is again the biggest conference in the world, IEEE Robotics Conference. And it was held in Yokohama in Japan last month. And there are over 7,000 attendees. And here we show live demonstrations in the exhibition site. That is, I think, very, very important. Not just showing the movie. Real robot demonstration is so actually the technical difficulty is a big difference. Showing not just showing the video or live demonstration, big gap between such a difficulty and also reliability, robustness, something like this. Here is one demonstration handling the laundry, picking up. Here we use only just 16 demonstration data. That is too small actually. So the demonstration itself is not so stable. at this time. But basically, we can see the success cases and it captures from the many media in Japan. Yes. Interestingly, it shows developed in only 2 weeks. But actually, it also includes a work to the move to the this container and pick up the dish. That is all the stories. But it takes a little bit long times. So here we just show these motions. And this robot is basically very expensive. Very, very expensive. So now I collaborate with Hitachi company to develop the latest version of the Moonshot project. So you see, so door opening robot. And the door opening robot is so not just for the door opening. It can be, of course, used for the many different types of applications. So we can develop this one is much, much cheaper than the original robot. And it can be trained very easily. Until the end of this month, I expect it will be released to the research purpose or more general purpose. Okay, so still have some time then. This is another example. So some of you feel that such kind of robot is very slow. Yeah. But here we show that that kind of robot can be moved very quickly. This is we collected just 3 motion data in the real world. That is augmented in the not simulator, but in the space on the data. We can generate different type of speed. Then the robot can enhance, adapt to the different types of object, also different types of motion, also different types of trajectory. So for example, this is just enjoys it. It's almost like the pet, but yes, this is trained very easily, and all the best paper award finalists in the IEEE conferences. And here is the last video. So yes, this is collaboration work with JAXA. JAXA is Japan Aerospace Exploration Agency. Yes, our application now enhanced to the space stations. So here the robot expected to support astronomy in the space stations. So during they take a rest or sleeping, the robot expecting to prepare the experimental settings or sometimes gathers such devices into the back. And here you can see we use the technique to the opening GPS. Yes. At first, just try to control the robot by using teleoperation, but due to the gaps, so actually there are time delays, so it's almost impossible. So we now here he is a researcher at Extra Wizards. That is one of the startup company, and I am now technical advisor of this company. Then they try to collaborate with JAXA for supporting this kind of activity in the space stations. Okay, so now then I think almost 90 minutes. Then sorry, just showing the many movies. So not talking about the details of my topics, but again, so my ideas is originally comes from topics, so such as psychological developmental robotics or cognitive robotics idea. So such kind of preliminary study, here I don't have enough time to explain the detail, but this kind of the research topics by modeling the human cognitive states in AI and robotics, Then that idea is directly the use of the application of the really robot hardware. That is my message now. Okay, that's all my talk. Thank you. Thank you very much. Then if you have any questions, please. Yeah. It's okay, any type of questions. Don't not related only my talk. So some of the topics related any types of topics AI and robotics, then I can say something.
Thank you, Professor Tetsuya, for sharing
Yeah.
knowledge and making this session much more valuable. We hoped our participants would walk away with invaluable insight into how deep learning technique may effortlessly interact with robotic system. So thank you, sir, again. Now it's time for a Q&A session. This session will be conducted by Mr. Peshan Sampath, Chairperson, IEEE Robotic and Automation Sri Lanka Chapter. If you have any questions, you can direct them to Mr. Peshan by using the chat box. The virtual stage is yours, sir.
Yeah. Thank you, Gitmi, and thank you very much, Professor, for like the valuable session. Like maybe for even though like we spent like 90 minutes, more than 90 minutes, like it was like just a like few minutes. I felt it like just a few minutes because like all the videos that you shared with us, like really interesting. They were like for me actually, they were like kind of like very good hyperlinks. So I got like few things noted down so I can do some research on them. So that's a kind of like a wonderful like opportunity for me as well. And thank you again. And then for again, like to start with the Q&A session, like I would like to like ask the participant in the audience just to share your the questions so we can maybe we can forward them to the professor and maybe we can have a kind of a like sort of like small discussion on them. Professor, like to start with the maybe Q&A session, like I have like a maybe like while I'm like listening to your session, I have noted down like a couple of questions. So maybe I'll start with one of them. Maybe as a one like Professor, like you mentioned about like during your session, you mentioned about like there were like a lot of training mechanisms, like a lot of training methods that we can follow. So one interesting method I saw, like when you're like opening that zipper in the bag, like the person like holding it and like maybe moving it. Maybe that's a one technique we can like teach the robot. So maybe can you like Professor, like could you please like explain, elaborate more on maybe some similar mechanisms so we can use to teach the robots?
Okay, thank you. One is so now, for example, Tesla, they takes away to the motion captures you, so now like the virtual games, and then detects in the hand position, then robot take. One way I understand, or directly make the kind of teleoperated machine so that each shape is similar, small size of the robot. Then it can move the robot to replicate its motion. So, or 3D mouse is it's just control the end effector position to teaching it. And each of them has some advantage and also disadvantages. And direct teaching, so by grasping with one arm is very intuitively is easy to understand what happened, what the robot actually doing. But it's not always the robot have such kinds of abilities. It can follow the human forces. And also, if we would like to teach the joint forces during the motions, so human grasping, that means the effects of bad conditions, the data is actually misunderstood. So in that case, open zipper cases, we just use the torque sensor equipped in the wrist pads. Then and the tactile sensor in the fingertips, so it can work. But some of them is a very difficulty. But for example, in the case of the Tesla, so handling the free spaces, so it's a very intuitively very hard to control the robot. So actually, so recognizing the mappings and such a free space arms, humans arms and robots, I always need to check the something. So very so not feedback to the target object, target tasks. So that is very hard. And now then I asked Hitachi to develop another type, of small type of robot. That case is so we can control robot using small devices which shape the same configuration of the robot. So it's also intuitively very easy. And Aloha, certain robot developed by the Stanford University and Google, they also take the similar ways. But it's also the difficulty to detect the feedback torque forces. So actually, there is no best way. Corresponding the types of the task, we need to select how to teach such kind of motion. But basically now they have many, some of the institutes have many experience to know about the use of the different types of device for the teaching robot. So I hope in the future they will show a more and more skillful, difficult task by human robots.
And at the same time, Professor, like, so anyway, like what we really need is like maybe many more maybe teaching methods so we can accurately teach the robot. So maybe that's what we need, like from all these methods, that's what we really need to teach the robots, I guess.
Yeah, right. Yes, another type of technology. So we just conventional robotics for sometimes, so it requires precise controls. But for the hard programs, of course, it often failed. But just to collect the data in the success cases, then the trend using such data is a network. Then the network deep learning beyond the original control methods. Yes, that is also one way. Also, when we noting the tying the no ropes task. In that case, is the original control system we conducted, but the success rate is less than 30%. But by collecting the success cases, so the deep learning shows over 90% success rate. That is also one way. So yes, actually there will be many different approaches.
Professor, like to move to like the second question from my end, like maybe before moving to the audience. Also, like in one of your slides, you mentioned about the balance between the software and the hardware. How we need to like have them in our robots, and like how we need to like do them in the future. Maybe Professor, maybe what sort of balance between like the software and the maybe the hardware we need to maintain for humanoid robots? Maybe a sort of like maybe what are like if maybe for an example, like if we have like a lot of like mechanical components and those stuff, like some like a little bit of like maybe software features in our robotic designs, so we might not be able to like achieve more. So maybe it's the vice versa as well. So maybe what sort of like balance we need to achieve between the software and the hardware when
Thank you.
developing the robots?
Yeah, good questions. Actually, so now I show the humanoid robot because we have the longest history was the development of human robots. So basically, Japanese like the human. And for imitating learning, teaching, so a human-like shape is much easier. So intuitively, it's understand what task the robot can do or not. So human robot is one of the solutions. But so as you mentioned, so balance is important. So Tesla humanoid seems to be quite expensive. Boston Dynamics as well. So maybe I didn't show them some slide, but some of them Aloha was such kinds of more cheap robot. Mobile and two arms robot can be also teachable by humans and such kind of skills. And I'm now thinking that there must be two ways. So one way is by developing this quite sophisticated human robot and try to teach many things. But as for the go to the marketing, so it should be simplified. So gradually select each function to keeping the balance of the AI ability in the robot. That is one of the directions. The other one is starting a more simple robot, like the delivery robot in the restaurant or a cleaning robot. So just mobility and with a small arm. Then that kind of the more cheap robot is gradually enhance its functions. So that these two directions might be one of the considering the story. So now our moonshot project has the IREX of quite large robot and also small cheap robots. So I try to both directions and try to find where is a good balancing on the hardware and the AI. Yes, that is a future plans, but and also very interesting target.
Yeah, thank you, Professor. Like maybe if we go to one of the questions from the audience, maybe
Thank
I got
you.
one question. Like maybe you also can like see that question. Maybe Dr.
Yeah.
Prabhan is like asking, how is the concept of lifelong learning applied to robotics using deep learning? How
Thank
is
you.
the concept?
Yeah. So then now then I think just supported human in many different scenery like first is public spaces might be easier for the school and hospital, restaurant, library. I don't know, but such kind of spaces there are many tasks always require power or sometimes dangerous, sometimes dirty or something like this. So repeat cleaning the toilet and washing, keeping the bed or something like this. That kind of task is will be the target of our robot. But so lifelong learning, that is more and more challenging. So not just train the skill, but also learning about the users or learning about the environment, which gradually changes, sometimes drastically changes. So such kind of adaptability is required for the robot which can work such a long times. And deep learning, current deep learning is so lack of such kinds of the functions. So once foundation model is developed, it can modify it slightly by adding such a fine tuning or something, but cannot change, cannot directly adapt to such a real environment. So like human is can developed gradually and continually learning, and the self-development can be done. But deep learning is still have some difficulty. So lifelong learning is now the entitled our project, but this is a very ultimate goal, like the dreams, 2050s. Firstly, now thinking is the first steps, try to develop the robot in the everyday life, and in firstly public space, and possible in the house and a more private space. So then gradually goes to the lifelong learning.
Maybe one last question, Professor, like without without going further, like maybe one last question from from the audience, like maybe how we can like ensure the safety of human, like when we are working alongside maybe humanoid robots, and maybe what sort of like mechanism that we are currently using, like like Professor, like maybe a few decades ago, like we were like thinking about the robots will like try to control the world, like because they will like get a lot of like maybe learning and they try to control. But still we are in the like 2024 and we are like still maybe like dealing with the robots, and we didn't like encounter such situations. Maybe what sort of like maybe uh safety like we need to like think about, like when you're developing humanoid robots and maybe when we are integrating deep learning. Any
Okay.
idea, Professor?
Yeah. So okay. So this is two aspects, so safety from the physically or information, right? And physically, so now, for example, we take the robot without leg. Because with leg means the robot has this possibility to fall down. That is so sometimes it becomes dangerous. And also that we added the torque sensors to all the joint, also tactile senses as the whole surface to avoid such a physically dangerous contact with humans. So I also show the demonstration basically done by robot by self. So no, with human can give the command, but basically a little bit separated. Because work with a very close situation sometimes could be cause such kind of action incidents. But at the same time, so we now think about support is elderly people, the handicapped people with physical contacts. So it could be a very challenging but an important target with needs considering the safety. But in future. And the other danger position is, so for example, the robot now have the camera. And the camera is automatically connected to the internet. Maybe we require some training data during such as supporting the human or conducting the daily life task. So, but is this cause a problem with the privacy or something like that? So now smart speaker usually don't have any camera. So now just only the voices. So we need to consider to the social acceptances. So which part is human can people can use it in a safe, in feeling safe. So of course we prepare the many protocol to keep such a security or the privacy. But at the same time, we need to advertise or show the more concrete technologies to keep the safety from the people, such as information controls. Yes. Yes, that is also now we often discuss with the researcher of the social scientists. Now they investigate it with a questionnaire in different countries. That is also interesting. There are cultural differences in the feeling of the safety about the robots. So now we try to make the stories could be commonly accepted in the world. That is also included in our project.
Thank you, Professor. Maybe if we have like any questions from the participants, maybe we can take like one more questions if we have time, or else we can wind up the Q&A session. Yeah, I believe like Professor, like we don't have like many questions with the time.
Yeah, thank
And
you.
therefore, I would like to hand over the session back to our MC. Nishadi will handle the session from here on. Thank you very much, Professor, and all the
Thank you.
organizers for and all the participants for joining with us.
Thank you. Thank you very much.
Thank you, Professor and Mr. Peshan. Professor Tetsuya, we are ready with a small token of appreciation for you, sir. Please accept it with most heartfelt gratitude. Okay, now there is a reminder of every participant. We want to hear your feedback about our session. So please fill the Google form shared in the chat box. Now I would like to Miss Michelle Pereira, Secretary IEEE WIE Sri Lanka section, to deliver the vote of thanks.
Think I'm visible. Okay. Right. So First, before moving on, I also should thank Professor Tetsuya because of the most engaging and also very interesting session. I also personally learned a lot. So thank you so much, Professor. And I'll do the formal thank you for everyone. So as we conclude this second session of Tech Pulse series, I would like to extend our heartfelt thanks first to Professor for his deepest session, engaging session. So I would like to extend my deepest gratitude to our guest speaker, Professor Tetsuya Ogata from Waseda University, for his enlightening session on design of deep learning for robotics and applications. So we are truly honored to have you with us today, and we appreciate a lot for your time and the effort you have dedicated to make this workshop quite a success. Next, I would like to extend my sincere thanks to IEEE Robotics and Automation Society Sri Lanka Chapter, and also IEEE Computer Society Sri Lanka Chapter for their collaborative support to this workshop. And next, a special thanks to our executive committee members and also executive committee members of both Affinity Group and both chapters, and also the volunteers of IEEE WI Sri Lanka section who organized this session with their hard work and making this workshop a success. And last but not least, I would like to thank our audience for your active participation and the presence with your enthusiasm. It has greatly contributed to this workshop really engaging and success. So this is the end of second session of Tech Pulse series, but we are looking forward to seeing you at our future events as well. So I would like to thank again Professor Tetsuya Ogata from Waseda University for your time and effort you have shared with us. So thank you again. Over to you, Nishadi.
Thank you, Ms. Michelle Pereira. Before concluding the session, we request all of you to switch on your camera to take a group photo, and we can use the virtual background we are dropped in the chat box. Can you please switch on your cameras?
I'll take the photo. Okay.
Okay.
Right.
Okay, thank you so much. So now it's time to conclude today's session. Thank you for everyone joining us with us. Wishing you success on your journey ahead. Have a nice day to you all. I'm Nishadi Visarayaka. Thank you.
Thank you, Professor. Thank you.
Thank you. Thank you. Bye.
Thank you.